Welcome to class today. Today we're going to talk about color spaces and a little bit about camera calibration as well. So last time we started talking about camera properties. So we were talking about, how cameras work and how pixels are read off of them. We also talked about the pinhole camera model and that the intrinsic parameters are really, the internal properties of the camera. And similarly, the other part of that is the extrinsic parameters. So this is basically what is going on outside of the camera. Or in other words, basically where it is in the world. So last time we talked a little bit about the intrinsic parameters. On Canvas, you'll see a link to a video on YouTube that talks about how you can use a MATLAB calibration toolbox to actually calibrate it. And the main thing is that, to do this type of intrinsic calibration, normally what we use is actually a checkerboard pattern. And what happens is that with this checkerboard, we know exactly what it should look like. So we know it should be checkered. And what can happen is that the actual software is able to then figure out if any of these lines are wavy or distorted in a way, then the software can then figure out the intrinsic parameters that will straighten it out to make it look like, so that the geometry is correct, so that we can actually use it to do computations on robot systems that have cameras. So today, what I want to talk a little more about is actually the types of colors and color spaces. So, we know that most cameras have, the RGB color space, so red, green, blue, and these are normally represented as, values from 0 to 255 for all these values. And the reason why this is 0 to 255 is that this lets us store it in 3 bytes, basically 1 byte each. And, this is kind of natural how we think about colors, how much red, green, and blue it is. But it turns out that if you change lighting, the values of the RGB values will change drastically. Whereas when we're operating robots, if we go into a dark room, we don't want the robot to stop working. We want the robot to still be able to detect, that red object or that blue object. So it turns out that there's a better type of color space, as it's called. Instead of just using RGB, which is what we're most used to, often in robotics, we use HSV color space. And what HSV is that the H is actually the hue, and this is basically how similar a color is to another. And then we have the S, so this is the S is the saturation, this is the colorfulness, and the V is the value, or sometimes known as the lightness of the color, and this is basically how bright it is. So basically what this lets us do is that when we have something of a similar color and we turn down the lights, basically what happens is the V value, the lightness value changes, but the hue and saturation do not change significantly. What this means is that we can actually, in our robot systems, actually be able to track how well, so we can track the colorful objects by actually just looking at the hue value and letting a larger range of saturation and value change. So there are many other color spaces. So there are color spaces that are metric color spaces, where the difference between, two values in the color relate to how differently humans see it, which is not true for RGB or HSV. If there's a very small change in the hue value for HSV, that'll look like a very different color than if there's a larger change in the value, the V parameter of the HSV value. So there are other types of metric color spaces that let you differentiate between colors, and then just all sorts of other like YUV. So there are many color spaces, but often you'll find that RGB is not sufficient for wanting to do some of the work we do in robotics, and that you often end up using color spaces like HSV. So you know that I love seltzer, so at my house I built a seltzer dispensing system so that I can replace these cans of seltzer with seltzer straight out of my tap.